Hey class, Adam Ward here. I'd like to talk with you tonight about the Streeter-Phelps equation, specifically how this can describe anoxic conditions, or times when we run out of oxygen in the water column. This is covered in lecture 21 in your Chopra textbook. And so the equations that we've used to describe these characteristic sag in oxygen downstream of a source of biological oxygen demand looks something like this. And as we increase the amount of BOD that would be coming from that point source, we can generate a larger and larger sag. Now, we run into a problem, however, when we make predictions that we could use up all of the oxygen in the system. And so the Streeter-Phelps model, as we've laid it out up until now, will actually let us predict negative oxygen concentrations. Now, that's not physically possible. And so there's some modifications that we need to make if and when we find ourselves predicting negative concentrations of oxygen. Right? When we get down to oxygen levels of 0 or near 0, we end up in this anoxic or anaerobic regime. And that means that the reactions that are taking place aren't really well described by that first order reaction rate that we've been using till now. So what actually does happen? And we know this from field observation. The first portion of our model looks correct. That takes us from basically saturated oxygen levels down to 0. But since oxygen can't be negative, we end up riding along the axis at oxygen equals 0. And then that lag extends further downstream than we would have predicted. So if we want to make accurate predictions, we need to find a way that we can account for this. That's the oxygen side of the story. At the same time, we've got a BOD side of the story. And so let me draw these vertical lines to help sort of orient us to where we start and stop at 0 oxygen levels. Now, in this first segment and this last segment that I'm highlighting in red here, exponential decay, our typical Streeter-Phelps equations, those work perfectly. The problem place in this is actually where oxygen levels equal 0. And so I'm circling that in green here and writing linear decay on the slide. And so we go from this exponential decay, characteristic of a first order equation, to a linear decay. That's characteristic of, you'll remember, a zero order equation, or one that doesn't depend on concentration. It simply depends on the time elapsed, how much we lose. So we're going to modify the Streeter-Phelps model to be able to handle this. And essentially we're going to use this model piecewise in the same way that we've worked our way down plug flow reactors with a variety of point sources and distributed sources a few weeks ago. So when deficit is equal to oxygen saturation level, meaning we've stripped all the oxygen out of the water column, that's where we need to apply this linear decay. Let me show you a little bit more in the next few slides. So again, here's our model of oxygen through time. And when we hit that 0 oxygen state, we're going to denote those times with a Ti and a Tf. So T initial and final is the way I like to think of those. And so in order to solve this problem, we want to first ask, when does the deficit equal that saturated oxygen level? When do we first predict that we'll cross the horizontal axis? And so we can use the deficit model that we have in Streeter-Phelps and simply set it equal to oxygen saturation level, which I've done on the left-hand side. Now, when you do that, you should know everything else in the equation except for that T. That's Ti. That's the initial time that we're solving for. Now, one thing to note, this equation has two solutions because, of course, that sag went down across the horizontal axis and then back up. Ti is the smaller of those two solutions. So you can solve your existing deficit model to get Ti. Sparing you some of the derivation, Tf is calculated by first finding Ti and then adjusting to the point where essentially the amount of oxygen coming in is equal to the amount of deficit being generated. So we've got this equation on the bottom in blue to help us calculate Tf. What you're looking at here is basically an equation that describes a zero-order reaction, and it does so until the flux of oxygen into the system, Ja as I'm denoting here, is equal to the consumption rate of oxygen in the system. So when those two come back into balance and eventually the deficit or the decay is slower than the oxygen supply, you'll start to build oxygen back up and you can pop back to that traditional Streeter-Phelps model that we were working on. Okay, one more time. Here's oxygen through space, and we can see where this becomes 0. If we break that down into 3 zones, before the 0, during, and after, denoted 1, 2, and 3. Zone 1 and Zone 3 are Streeter-Phelps equation, just like we've always done it. In Zone 2, we've got oxygen levels equal to 0. So that's what we would do for oxygen. For BOD, same story, Zone 1 and Zone 3, typical Streeter-Phelps equation. But what we're going to do in Zone 2 is, again, use that zero-order approximation. So we'll do BOD as a function of t, travel time, and you can, of course, substitute in velocities and distances instead of travel times if you want this in the x-axis, in the spatial domain. That's equal to Li, so the BOD, at that transition from 1 to 2. So the BOD when the linear piece starts, minus Ka times that saturated level, times how far you've moved to the right. And you'll notice that's basically in the form of y equals b minus mx. Right? So a linear equation. During that linear portion, again, just to point out to you, the decay is only as fast as oxygen can enter the system. So in Zone 1 and Zone 3, you're decaying away essentially as fast as you can. There's always an ample supply of oxygen. So you're limited by essentially the rate coefficients there. When you get to that Zone 2, the linear chunk, you're basically limited by how fast oxygen can get from the atmosphere across that boundary layer and into the system. So the mixing in the system itself, the reaeration rate, ends up being what limits that zero oxygen, that linear BOD decay section of our system. So after watching this video, you should be able to describe why the Streeter-Phelps equation breaks down at that oxygen equals 0 level. You should understand how to find where that will start and end, Ti and Tf, and you should be able to calculate deficit, oxygen level, and BOD concentration profiles in space. Again, this is downstream of a point source into a plug flow reactor. Thanks everyone, and I'll see you in class.